Welcome back, chemistry fans. We are going to pick up where we left off last time. We're in the middle of our kinetics unit. So this is topic number 2. Let me share my screen and we will get started on talking about how we can manipulate reactions. So in the previous topic, I just shared with you a Maxwell-Boltzmann curve. And that Maxwell-Boltzmann curve has an activation energy over here. Well, what if we somehow were able to move this energy line? Well, then I would have more particles taking part in the reaction. That would be awesome if we could make that happen. Or what if we shifted the line and made it look a little bit different? So this is what we're trying to manipulate and show with the effects. So we need to understand that there are 5, if not 6 ways in which we can shift that Maxwell-Boltzmann curve and make the reaction occur faster. The 6th would be the inclusion of volume in here. So we can make particles smaller. We can add more particles. We can get the particles closer together by changing the pressure or volume. We can increase the temperature, make them move faster, or we can add a catalyst, which its whole job is to lower the activation energy. So let's investigate these on an individual basis. So surface area. How does surface area speed up the reaction? It makes the molecules have more reaction sites. So it just simply breaks up a chunk of material into smaller pieces, and it means that it's easier for the reaction to occur, as you see in the images. Some examples of this is something called a catalytic converter. It is in every one of your cars, and what it does is it forces all of the exhaust in your car to go through reactors, and they have activated sites, which have, you could see these honeycomb areas. And as it passes through, some of the bad particles stick to the catalytic converter. Another example of this is if we have a block, it is only going to react on the outside surface. If we break up the block into smaller pieces, every single surface has more opportunities for it to be attacked. What this looks like on the Maxwell-Boltzmann curve is that you notice what I have done is I have just increased the number of particles. So therefore, where we had the number of particles was small, now we have a much larger area because I have increased the number of particles. So my Maxwell-Boltzmann responds to that. Now, concentration. What happens if I change the concentration? It's going to look a whole lot like what we just did on the Maxwell-Boltzmann because we are adding more particles. So it has the exact same effect on the Maxwell-Boltzmann that this one did because we're adding more particles. Examples of this one is shown here that we can simply cause sodium thiosulfate and hydrochloric acid. If we add more, we could speed up the reaction. Zinc and hydrochloric, the more particles I put in, the faster the reaction goes. So that's all that this is showing here. Going left to right, if I add more blues, I get more reaction. If I add more reds, I get more reaction faster because they can attack the particles. And that's what you're seeing here is that if I increase the number of blue particles, there's more available for the greens to attach. And so you have more collisions and you have a faster speed. Again, what occurs is that if we increase the number of particles up to that green line, the activation energy stays the same, but the number of particles has increased. The shaded green is larger than the shaded blue area. All right, pressure. If I get the particles closer together, they have less room to wiggle, and therefore they have a better attempt at falling in love, causing a reaction with the particles. And so what we have here is that we should see the end result is that we are increasing the speed of the reaction. The Haber process is one of the fantastic examples showing this, that if we compress the hydrogen and nitrogen, the reaction will happen faster because it's producing the products at a faster rate. So whenever I have a higher pressure, again, what we are doing is we are pushing the particles closer together. It appears that there are just more particles, but it's because they're being pushed together. Now, here's the interesting thing. There is no change on the Maxwell-Boltzmann graph because We don't change energy. We are not speeding up the particles. We are not adding more particles, so neither of those are reflective on this graph. So the Maxwell-Boltzmann, you can't see a change whenever we change the pressure and volume. All right, temperature, we can see that on the Maxwell-Boltzmann. So all we're doing with temperature is we're increasing the speed of the particles. As particles get hotter, they move faster. So the rate of reaction is going to increase because the particles move faster, which means there's more chance that they're going to collide with another particle. And that's being reiterated here. Now, the Maxwell-Boltzmann graph on this one, what happens is the higher the temperature, the more it shifts towards the right because the average temperature has shifted. Notice the average temperature here was low. Now the average temperature is a little bit higher, the mode temperature, rather, I should say. And so what that does is it causes more particles to have enough energy to cause the reaction. So it's not that I'm moving the line up to cause more volume. I'm moving it over to the side to cause more volume on this graph. And then finally, a catalyst. A catalyst lowers the activation energy, which speeds up the reaction. So on the Maxwell-Boltzmann curve, what we should start to see is that the activation energy shifted backwards because this is on the x-axis, a line dealing with energy. So if I lower the activation energy, now I have increased the amount of particles that can react because it doesn't take as much energy to cause a reaction because I've added a catalyst. This is everything that I wish to share with you today about the 5 different ways, maybe 6, that we can start a reaction, make it go faster. So thank you very much for staying together. I will talk with you again soon. Bye-bye.